Scalars have magnitude, no direction, and they obey the laws of ordinary algebra, right? Scalars. First example is distance travelled. Distance travelled is a scalar. Speed is distance travelled per unit time is a scalar. Temperature, pressure, both are scalar quantities, right? Pressure is perpendicular force by area, normal force per unit area is pressure. Pressure has got a direction which is unique, so pressure is a scalar. Mass is a scalar. Energy, all kinds of energy, potential energy, kinetic energy, all are scalars. Work done is a scalar, right? Anything having the word potential, like electric potential, magnetic potential, all are scalar quantities. Electric current is a scalar. Some of you may start thinking how electric current is a scalar, right? We give arrow to the flow of current. But if a current of 3 ampere is going like this and a current of 4 ampere is going like this, always we get 7 ampere. This does not depend on the orientation of these wires. You keep on changing the angle, still you get 7 ampere. So electric current does not obey the laws of vector algebra. So electric current is a scalar. So all these are scalar quantities. Now let us look at vectors. Vectors have got magnitude. They have got direction. And they obey the laws of vector algebra. That is important. Okay. So we start with displacement. Displacement is the first vector that we can think of. Displacement per unit time is velocity. Velocity is also a vector. Rate of change of velocity is acceleration. Acceleration is a vector. Mass into acceleration is force. F equal to ma, Newton's second law. Force is a vector. Mass into velocity is momentum. Momentum is a vector. Force into time is impulse. Impulse is a vector. Torque, the turning effect of a force, is also a vector. Torque is force into perpendicular distance. Suppose this pen can rotate about this hinge, we can say, right? If I apply a force like this is creating some turning effect. That turning effect is called torque. Torque is a vector. So remember these examples systematically, then you'll not forget. Vectors, first you think of displacement. So displacement is a vector. Displacement by time is velocity, that is a vector. Rate of change of velocity is acceleration, acceleration is a vector. Force is mass into acceleration, that is a vector. Mass into velocity is momentum, momentum is a vector. Force into time is impulse, impulse is a vector. Force into perpendicular distance is torque, torque is a vector. Anything having the word field, that kind of physical quantity is a vector. Electric field is a vector. Magnetic field is a vector. Gravitational field is a vector. All these are vector quantities. Now, there is a quantity called finite angular displacement. Okay, that's a quantity that we learn in rotational mechanics chapter. This finite angular displacement, what does it mean? If a pen is like this is a zero angular position. It moves from here to here. It does move by some theta. That we call it angular displacement. Finite means it is not very small. This Reasonable. Okay, that finite angular displacement is not a vector. So remember this, finite angular displacement is not a vector because it does not obey the laws of vector algebra. This you have to learn in detail when you study rotational mechanics chapter. For the time being, remember, finite angular displacement is not a vector. Important to remember, anything having the word potential is a scalar, anything having the word field is a vector.